Okay, perfect. We're gonna start up. So, hello everybody, welcome to this AJS. Today's speaker is Michele Cogo. He's a PhD student at University of Padova under the supervision of Professor Francesco Picano. Well, among the many things that he's working on today, we'll present a little bit about, let's say, hypersonics in general, highly compressible boundary layers. So I don't want to speak too much about the presentation. So without any further ado, the floor is yours. You can start the presentation.
Yes, thank you. So hi everyone. So today we speak a bit about the physics and the modern aspects of highly compressible boundary layers. And then if you have any question, you can interrupt me or ask me later. So a bit more about me. So I've studied at the University of Padova, and then I've done a brief period of research at the Sapienza University of Rome. And then I started my PhD at the University of Padova, and I had the opportunity to do to visit two beautiful universities such as TU Delft and Stanford, and where I met a lot of new friends and colleagues. And I've been part of the Fulbright program. So if you have any question about that, maybe later we can talk, and it's a very good opportunity for all the students. So in general, my interests are mainly in turbulence and compressibility. So I've been very passionate about these topics. And I really like the fact that they entangle a lot of different aspects, such as they have multi-scale structures. There is the nonlinear dynamics embedded in the Navier-Stokes equation. There is a strong mixing between the quantities due to the turbulent effect. And then a very cool feature about compressibility is the shock waves. So you do have a lot of different, you can have a lot of different shocks in different part of the flow. So these aspects are present in a lot of different applications like planetary reentry, atmospheric flight, orbital flights, and suborbital flights. In general, what I study is applicable to the region near the solid boundary. So I'm mostly focused on hypersonic flight at high enthalpies and relatively low altitudes, where you can have the onset of turbulence. So you can see that here there is a cartoon of a wedge. You have the transition from laminar to turbulent on the boundary layer. Then you can have large Mach numbers, and that generates large temperatures and intense variation of thermodynamic properties. And then in certain cases, when you're flying really at high speeds, you can have even the activation of thermochemical processes. So you can see here a cartoon of a different profile that among velocity and temperature, you can also find different variation of the mass fractions of the chemical composition of air. So you can have different quantities appearing and disappearing depending on the local temperature. And the fact is that all these phenomena are coupled together, and they participate to the complexity of physics together. And there is this phenomena called aerodynamic heating, which is really interesting in the hypersonics, and I'm going to talk about a bit of this in the next slide. So in general, the presence of turbulent, hot, and highly compressible boundary layers increase the mechanical and thermal loads of the vehicle. So we must study them to inform design choices. So I want to talk a brief moment about this phenomenon called aerodynamic heating. So you can imagine that you can have a solid boundary with a certain wall temperature, and then another useful temperature to define is the recovery temperature, which is very similar to the stagnation temperature, so the temperature that the fluid reaches when it's close to rest by the friction with the wall. But since this process is known as entropic, there is a recovery factor R, which is usually 0.9. So you can think about it as a stagnation temperature. So let's do some experimental thoughts. So you can have a solid boundary, and you set free state temperature. And when you have, for example, supersonic flow, the flow will, the temperature profile in average will settle to a certain temperature, which is the recovery temperature, which is, for example, at Mach 2, 1.7 times the free stream temperature. But as you go higher and higher, in the Mach number, you can see how this temperature is extremely high. And you can have a very high temperature near the wall that, of course, generates large heat fluxes. This is, of course, something that we do not want, because we would like that the material that the surface is made that can resist. So usually we try to generate an active or passive cooling, so to decrease the temperature of the wall. So in practical cases, the temperature profile look more like this. So you can see that the temperature profile would like to settle on higher values, but it's forced to turn and to obey to a certain temperature that is imposed at the wall. And this means that you have a formation of a local peak. And this is the most interesting case, and the case where the aerodynamic heating is generated, because the friction of the flow with the wall transforms the kinetic energy into heat, and this heat is from the flow to the wall transferred, and it's a problem. Then you can, as a thought experiment, increase more and more the wall temperature, but you will encounter even higher temperatures. So this is relevant for some results that we will see later, and it's an interesting fact of the hypersonic flows that you have a non-monotonic behavior of temperature near the wall. So as just an example, this is an example of the Concorde at Mach 2, and I taken some data from I guess the wing. And you can see that the wall temperature is very similar to the recovery temperature. So this ratio, when it's near 1, means that you have an almost adiabatic condition, so the temperature release is almost 0. So in this case, you do not have to worry so much about the aerodynamic heating. Hence, you do not see tiles or protection systems on the type of aircraft. But as you go higher and higher as the Mach number, or for example, the velocity, you must be aware of the fact that the heat flux is proportional to the velocity cube, in contrast to, for example, the drag that is proportional to the velocity squared. So there is the so-called heat barrier that sounds like the sound barrier, but it's another type of barrier that happens when you approach hypersonic speeds that really puts at danger the thermal resistance of any aircraft. So going to back to another type of quantity, this is the velocity that maybe we know better. Let's start from incompressible flows. So incompressible flows, we know that the velocity profile on average, when it's rescaled with viscous units, settle into a certain profile that is considered with universal behavior. And in general, we consider this profile made of 2 laws. So the first law is the linear law that starts from the wall. And then we have a logarithmic region that is a law that has become one of the fundamental part of the study of turbulence, and you can generate a lot of models thanks to this universality. We have a problem, however, in hypersonic flows, because the effect of Mach number and the wall temperature and so on do not allow the velocity to obey to these laws in a strict sense. So there has been some hypotheses, for example, the Markov hypothesis, to try to take into account the variation of mean properties, such as density and viscosity, that we know that in incompressible flow they do not vary, but in compressible flow they do. Taking into account this variation, we could try to map the compressible profile into the incompressible counterpart, and try to use once again these laws that are also useful. So one example of this compressibility transformation is the Van der Waals transformation. And a brief explanation of this transformation is that if you consider the log law, so if you integrate this law in its a logarithmic function, and you can recognize u tau as a friction velocity, and you consider also the compressible counterpart, where you can see that density can vary. It's not the value at the wall. You can think that this law makes more sense with compressible flows, since as the density is varying. And but you would like to try to make a connection between this gradient, this velocity gradient, and this other gradient made for incompressible flows, to try to use these laws that I just talked about. And if you try to come up with a relation between these two gradients, you're doing a compressibility transformation that in the example of Van der Waals was just a matter of rescaling with the density. There have been in recent year much more complex relation proposed. For example, Griffin and others proposed a very good relation just a few years ago. But the whole overall concept is that you want to recover the behavior that we do see in incompressible flows by taking into account the variation of mean properties of the flow. So the open question that I'm going to try to answer in this talk is that from a physical perspective, we would like to address the effects of Mach number and wall temperature in high-speed boundary layers, and maybe see if this compressibility transformation can work to recover the expected behavior of the mean velocity. And then another question that maybe now it's not so clear, but I hope to make it clear in future slides, is that the degree of wall cooling or wall heating, so the aspect I was talking about before of the fact that there is a peak in the mean temperature, is something that is important to define properly, because it can vary both with the wall temperature but also with the Mach number. So I'm going to try to address this question. And then we're gonna address some more modeling perspectives. So I'm gonna talk about the state of the art of wall modeling for high-speed hypersonic wall bounded flow. I'm gonna try to make you see how the compressibility transformation can be used to develop these models. And then we're gonna further delve into more complexities of this physics by taking into account chemical reactions triggered by the automatic heating. So in general, I want just to stress that the first part will be about direct numerical simulation, so we can afford to talk more about physics, because we have confidence that the simulation can resolve all the scales, but they are still calorically perfect gases. But in the last part of my presentation, I will talk about models with reacting mixtures of thermally perfect gases. So we're gonna see even some application where the temperatures are so high that the chemical reaction are activated. So let's start with the first part. The first part is, of course, in collaboration with my supervisor, and then with Professor Bernardini and Chinappi from Sapienza University of Rome and Tor Vergata. And then with this collaborator, we developed several databases in direct numerical simulation. Here I'm going to present one of one such a database, and we use the solver Streams, that is an open source solver oriented to modern HPC platforms that can be parallelized both with CPUs and GPUs. We use the cluster Marconi 100, and just to give you a sense of how expensive these simulations are, some of these simulations require up to 28 billion nodes. So they were really, so you can see why even the need of creating wall models. So the database I'm going to present consists of 12 cases at a fixed Reynolds number, but varying the Mach number from 2 to 6. And the diabatic parameter, which is a parameter that takes into account the differences in the wall temperature with respect to the free stream temperature and the recovery temperature, with 4 values for each Mach number. I'm going to try to explain why we decided to fix this parameter and not the more obvious wall to recovery temperature ratio that I used before in the Concorde example. But for a moment, let's just see the major differences. You can see from Mach 2 to Mach 6 how drastically the density field changes. There are a huge variation of density, of course, in the hypersonic case. And then we can see try to see what I explained before regarding the velocity profile. So you can see here that it is in blue an incompressible profile that agrees very well with the log low. But as you go higher and higher in the Mach number, you have a more pronounced mismatch. These are just for adiabatic case, but so theta is 1. But if you go in the cold wall condition, you have even worse results. So let's try to see the boundaries transformation in action. So you can see that there is some sort of recovery of an agreement with the log low, but still the hypersonic case is still not fully in agreement. And for instance, I mentioned before the Griffin-Others transformation that is a recent transformation that has been proposed. And you notice that it's not only the velocity that is rescaled, but even the one normal coordinate. So the profiles are shifted. So, but there is an excellent agreement of the log low for all the profiles. So you can see by looking even at the date, the year that was published, that there is a huge interest in this compressibility transformation for this reason, because when you can recover an expected behavior that is universal, you can apply one models. We can go back even to temperature profiles. So you saw the cartoon before. Now you see the DNS results that I told you about. So this is the very pronounced change of temperature when you go higher in the Mach number. And then when you fix the Mach number, for instance, to 6, you can see how the temperature profile changes from having no peak, obviously, because this is an adiabatic condition, to having a more pronounced peak. And another interesting point is that the peak gets higher in the one normal direction as you go with colder temperatures. And this is something that we were interested in because, for example, the use of the adiabatic parameter is important in this sense. Because when we fix the wall to recovery temperature ratio, we noticed that we were not obtaining expected results. And instead, what really mattered was the difference, this term, the kinetic term that can be converted to thermal energy. And you can see from Mach 2 to Mach 6 that you can, if you fix the same wall to recovery temperature ratio, the adiabatic parameter is really different. And let me show you what changes. So for example, here, there are all the profiles of temperature in all the 12 cases. This is called the coldest case, this is the adiabatic case. And you can see that by fixing the adiabatic parameter, even if there are different intensities going from Mach 2 to Mach 6, but the location of the peak is almost the same. And obviously, you do not see this behavior when you fix the wall to recovery temperature ratio. So it was important for us to select these parameters to kind of see the same general behavior across different Mach numbers. So we could also try to see some sort of scaling. And so we can say, without the regard of the Mach number, the peak will be approximately at this location. So let's keep in mind this location of Y star almost 10, because in the next slide, I will show you some slices parallel to the wall of temperature and velocity fluctuation at this location, the Y star 10. On the left, I have the coldest case at Mach 2 to Mach 6, and on the right, I have the adiabatic case. And you can see the first thing that I want to stress is that once again, thanks to this, fixing this adiabatic parameter, we see a similarity of comparison between velocity and temperature in the coldest case, and in adiabatic case, we do see similar features. And more importantly, when you have very cold case, it seems that temperature fluctuation are almost non-existent, while velocity fluctuation, they are apparent and they are correlated in the space in the form of streaks. While in the adiabatic case, you see a very strong similarity between the two fields. You can even spot the same patterns. So we wondered, why is that when you go to colder temperatures in the boundary layers, the fluctuation of temperature become almost not non-existent, and they're very much damped. So we tried to investigate it, and we saw this fact even in the RMS of temperature. You can see that as you go colder and colder with the wall temperature, you see a damping. And when you see around the value that I showed you before, where I took the slices, you can see a minimum being apparent. And there is the interesting feature that the local maximum is present near the wall. So we were interested by trying to understand and come up from a physical explanation of this behavior, because you start with a monotonic behavior to the wall, from the wall with the adiabatic case to a non-monotonic one. So we tried to come up with an explanation for this, and our explanation takes into account the generation of temperature fluctuations by means of the thermal production, which is similar to the production of turbulence. You have a turbulent air that is a correlation between velocity and temperature, and then you have the mean temperature gradient. So our understanding of the phenomena looks like this. So in the adiabatic case, if you go around 10, you can see that you have a gradient. Here it's exaggerated, but if you think that you can have a certain temperature T1 that get transported upwards to another location, it will find a very different temperature T2, and you will have the generation of temperature fluctuations. Instead, if you look at the same spot, but for the wall cool case, you can see that when you go from one temperature to the other, transported by a certain velocity fluctuation, you will not find a very different environments. And this is our explanation why you do not find the temperature fluctuation. And this is also visible in the profiles of this term. You can see that the production of thermal energy is very much damped near the wall. And a local maximum is present here. And the reason for that is that if you apply the same reasoning of a gradient being present, you can see that there is a gradient here below the peak location for the very the coldest case that generates a local peak in temperature fluctuation. So in general, we discussed these effects related to the Mach number and wall temperature, and we observed these phenomena of the damping of temperature fluctuation due to the wall cooling. And we tried to also give an explanation of this secondary peak that we just discussed. We also had a lot of different discussions that are not being discussed here, but if you are interested, there are two references, or you can also ask me questions now or later. So now I'm going to proceed with the second part. If you do not have any question, urgent question. And so the second part is we will make a shift to wall modeling. This is a work that I've done at Stanford when I visit Professor Parvitz Moin, and I collaborated with Dr. Kevin Griffin and Christopher Williams. And in general, since we now shift to wall modeling, we have to justify why we want to do this. So in a broad sense, the problem with wall bounded flows is that the energy containing scales near the wall are the ones that are very small. So both LES and ENS have similar computational costs because you do have to resolve each scale at the wall. So there is some hope for wall model LES because it promises a linear dependency with the Reynolds number of the number of computational points. So the concept is that you want to have your LES simulation in a Cartesian or whatever grid you like, but from one point below, you do want to use a model instead of resolving all the scales. So there will be a matching location at a certain height that gives input to the model certain quantities. And as an output, you will inform the LES solution with the shear stress, the heat flux, and other quantities you may want. The most famous wall model that is used in wall bounded turbulence is the equilibrium wall model. That is essentially Raman's equation, so the average equation of the Navier-Stokes equation, but with some some assumption, and given thanks to this assumption, we reduce this equation to ODEs, not PDEs. For compressible flows, you do have to carry even the energy equation, of course. Otherwise, you would have only the momentum equation. And you can solve them in a separate grid and compute from this equation the velocity and temperature profile that you can use to compute the shear stress and the heat flux. And I want to stress that these are variable properties in compressible flows, so the viscosity will depend on temperature. The eddy viscosity will depend not only in Y, but also in temperature, density, and so on. Another idea that has been proposed very recently is that you could use the momentum equation like it's used in incompressible flows with constant properties. So you assume temperature, density, and viscosity constant, and you will obtain from this some sort of incompressible velocity gradient that you can now try to transform back to the compressible counterpart. So we just said before that compressible transformation map a compressible profile into an incompressible counterpart to have an agreement with log law and so on. And here you use use them in the inverse sense. So you want to map the incompressible gradient into the compressible one, and then you can use an energy equation to solve for temperature. And since there has been a lot of work with compressibility transformation applied to high-speed flow, this type of relation gives rise to much better results for high-speed flows compared to the equilibrium wall model. And here I'm still talking about a formulation for calorically gases. So you can see, tested on the data that I just presented, the GFM model has much better result. More specifically, when you have the cold case, that is the toughest one to model, mostly for the reason I explained before, that there is a temperature peak here, you can see that it has an improvement over the equilibrium wall model. So my work at Stanford has been devoted into using these models, but applied to when you have very high enthalpies and chemical reactions. So you know that I just speak about a lot of this aerodynamic heating phenomenon, but we also want to take into account the dissociation recombination processes that are in place when there are very high temperatures. And another important aspect that we ought to take into account is that the chemistry is not in equilibrium with turbulence. So the time scale in which chemistry happens are similar to the time scale of turbulence. And for this reason, you cannot consider the chemistry as frozen, for example, or in equilibrium, as a lot of different applications instead do. So we want to develop wall models for this application because we want for sure to shorten the time to solution and tackle complex configuration. And to do this, we use the DNS dataset of Williams and others. And you can see that the year is just last year because dataset of this kind were not computed since very recently. And moreover, the dataset is very useful to develop models because it has a Reynolds number that is fairly high, a Mach number that is extremely high, so we have Mach number of 20, and then we have extreme wall temperatures at the wall. And to give you a sense of this environment, the temperature is so high that the molecular oxygen that is naturally present in the air is almost entirely dissociated near the wall. So you have a very active environment in the chemistry sense. So this is a cartoon that is representative of what I told you before in the wall modeling. We have a matching location where we sample the field with certain quantities, and we want to output other quantities like the shear stress, the heat flux, but even the mass fraction of air, because they do vary at the wall. So we try to extend the GFM model, that is what I told you before with the inverse velocity transformation, to make use to solve for the species partial density equation. So we have an equation that carry all the mass fraction of air, and with this term we take into account all the chemical reaction. And this work is a work that was inspired by another work of Direct and others that extended the equilibrium wall model in a similar way with a species partial density equation. But both models have been tested for the first time in an a priori sense in a reactive boundary layer, since it was not available at the time. I just want to mention briefly the species partial density equation, since it's something that I know it's a bit complex, but essentially there is a term accounting for the laminar diffusion and another one for the turbulent diffusion. And the most important term that we want to care about here is the chemical reaction rate. So this is the term that makes chemical compound appear or disappear as a function of the temperature. So you have a certain temperature, maybe it activates some chemical processes in the distribution of the mass fraction and the density at that point. But one very tricky point to consider is that this quantity does not depend only on the mean values of these quantities, but also in their fluctuation and correlation. So you can see that when you just compute this term only accounting for the mean quantities, you have the dotted line, and with the solid line it is the whole average term in DNS. So we did this assumption because we did not have other choices. But in general, we know that this is a strong assumption, and the turbulence, the reason why this profile do not agree is because turbulence creates a lot of fluctuations. So in general, we see that we had better results with the extended version of the GFM model in red compared to the equilibrium wall model. And we did improve the prediction of shear stress and heat flux. But we had some difficulties in predicting the mass fractions. You see that, for example, this is nitric oxide, molecular nitrogen, and atomic nitrogen. You can see that both at the wall and even in the gradient near to the matching location, we do not fully agree with DNS data. And we wanted to confirm what's the leading cause for this to inform future works on this topic. So we had, you cannot see, but here is assessment of turbulence and chemistry interaction. And we had suspect that this term, the chemical reaction rate that I just explained, was the leading cause of errors. So we imposed the DNS profile of this term into the whole model equation as known quantities, and we recovered very good agreement with DNS data, and even a better agreement with our model in red than the equilibrium wall model. So we were confident that this is the direction we should work on to try to better model this chemical reaction rate to take into account fluctuation of quantities. So in general, the final remarks of part 2 are that we propose an extension of a present model that has been a lot of success for high-speed flows, but they was not formulated to include the multi-component reactive mixtures with final rate chemistry and differential diffusion. And we had we saw some improvements compared to the previous work that extended the equilibrium wall model, having better results in the velocity temperature profiles and in the prediction of the shear stress and the heat flux. But both models have some difficulties in predicting the mass fractions with minor differences between each other. Since we saw that there were minor differences between each other, we thought that there was a big assumption for both of them that was the leading cause of errors. And this assumption was the modeling of the chemical reaction rate. It was modeled only with the mean quantities. And this was discussed in a brief that was published, has just been published as part of the CTR annual research brief of 2023. So in general, the take-home message, and I'm going towards the conclusion, is that the dynamics of high-speed boundary layer is complex, and I tried to inform you about the presence of the effects of Mach number and wall temperature that are very significant in hypersonics. And one very important aspect of these effects is the generation of the higher-level heating. That is something that we want we want to know this phenomenon very well to inform design choices. And then I tried to make the case why we do need to care about a specific wall cooling parameter that can obtain the same general behavior across different Mach numbers. So, for example, the parameter we used had the feature that you could see the same peak location in the wall normal direction across different Mach numbers. Then in the second part, I talked about wall modeling for high-speed flows that received a lot of interest in recent year, thanks also to the development of compressibility transformation. And thanks to this compressibility transformation, we tried to extend the GFM model, accounting for high entropy effects with good results compared to the previous works. And then we confirmed that one main bottleneck when you're trying to work with the chemical reacting boundary layers is the modeling of the chemical reaction term. So we want to understand how to solve this problem, and we know that this problem is very present, for example, in the field of combustion. So with this, I've been a little bit fast, but thank you for the attention. If you have any questions, I'm glad to answer.
Thanks for the presentation. Really, like, be honest, pretty impressive. Really like it. So yeah, if there's any question on the audience or online, yeah, you can go ahead.
I have one question, one curiosity, and two. No. The first one
you can ask three if you want.
Yeah,
that'll be fine.
The first one is: have you never thought to correct the chemical reaction rate by a data-driven technique?
By also
A data-driven technique?
Yeah. This is something that we thought. So I know that in combustion, this is something that it's really used. In general, the really tricky part about this term is that sorry, let me go back. No, yeah. So the really tricky part is that usually with a data-driven technique, you can think that, for example, the temperature variance is what varies the most. So if you do take into account with a data-driven technique, you have several cases. You can learn the model to understand if you have a certain degree of temperature fluctuation, you will it will respond in a certain way. This works, but the really tricky part for us is that all this fluctuation matters and all this the correlation. So all the demand terms in the matrix will be important. So you will need a ton of different DNS dataset, and at the moment we have like three DNSs to work with.
And I remember that it took quite some time to have all those profiles to be converted. So
a lot of DNS and a lot of headaches too. So the point for us is that we do not have these reliable datasets to use. So we have to be informed by physics more than data.
Okay. The second one is just out of curiosity. What type of space discretization have you used in your simulation?
So in the DNS simulation, we use the resolution that you use with DNS. So you go down to below the Cogo scale, and we resolve the flow with, for example, at the wall we have a y plus of 0.5, and we have a certain stretching function in the boundary layer that allows us to resolve all the boundary layer with the necessary hooks.
Okay, but finite difference.
Yeah, sorry, finite difference. Yeah, we have high order finite difference.
yeah, maybe I can add to this question because like it's related, let's say. The final difference is like energy preserving in
Yes.
terms of kinetic energy.
Yes.
Is it also like entropy preserving?
No, at the moment it's just energy.
Okay, okay. And no, yeah, you get there. Because I another one plans with, but later on.
I mean, is it the same thing that this guy at Imperial is doing it, Peter Vincent, right? Is it has the pi for library? Do you know this?
By far, yeah, I know the library, but you mean like the
I also like the higher order finite difference scheme.
it's a thing in general, like doing high order with like charts, standard order. It's like it's kind of entropy preserving. Yeah. In that case, it's finite volume, but they do entropy preserving finite volumes.
See, I wanted to understand that this one of them is this question. So, but before I come there, first thing I wanted to understand is the extension of the Griffin model.
Yes.
I probably missed it. You might have showed it. So, what is the extension of the Griffin model?
So the extension is that it has been formulated for calorically perfect gases. I did not go into the details. Oh, sorry, I'm going in the other direction. But I did not go into the details of how the model is formulated because I know that it's still a lot of different things. But in general, I wanted just to pass the message that the Griffin model has this inverse compressibility transformation for the momentum, but for the energy, it has a temperature velocity relation that we changed into an enthalpy velocity relation because we do not have a linear dependency with temperature and enthalpy. So we changed one equation of the model, and then we added the species equation that we're still going back and forth. But so we coupled the model, the present formulation, with the species partial density equation, and we had to try to come up with a lot of different modelings for all these terms. So the extension was in this sense, yeah.
So you have not shown it explicitly, but I see the idea. But then, is this your species transport equation?
Yes.
Or is it just at the near world region?
So these are a priori analysis. So we are solving for this equation for the near world region, and we are trying to match DNS data from a matching location that is given. So, for example, here you see that the model matches perfectly with the DNS because we impose the temperature at this point, and then we solve this equation that I showed you throughout the whole.
Yeah. The reason I'm asking is because generally some of the species equation I've seen, they look like the momentum equation, like the full thing, but except for this u variable, which is the transport, you have a species. Species. So are you using that equation or some form of equation?
Maybe you are referring to more of a passive scalar transport. So
something like that.
Okay.
That also can be
So our point is that we are still transporting a variable, but here there is a source term. So we have final rate chemistry. So the variable is not only transported by the fluid, like it can be a passive scalar, but it's actively changing the fluid with chemical reaction that are changing the composition of the fluid in that spot. So this term is really changing is different from a passive scalar equation.
Okay. So this is the ultimate equation that you are solving. There is no more another equation.
Well, there are a lot of different assumption models underneath all these terms, but this is the equation.
How do you get this term Ut?
This is the eddy viscosity. This is a model for the Reynolds stresses, and we have the boundaries formulation. So that is the I don't know if you have
the power.
Yes, with the exponential decay at the moment.
I see. So okay, so that's basically Ut is one risk type damping.
Yeah, actually, it's not really. So this is the way we do it when we use the equilibrium model. But we found a smart ways to not use the formulation, the conventional formulation of the μt for the GFM model, because thanks to the fact that we are using a compressibility transformation that I just showed you, we can obtain the μt from the velocity gradient that we just got from the compressibility transformation. So we can bypass the conventional model of the mixing length hypothesis for the viscosity. I know that I can go more in detail in this, but maybe we go too fast.
Yeah, I can see that like it would take some time to go up, but I mean, I'm following as well. I think I got the idea.
But okay, we can discuss this offline.
Yes,
This
sure.
particular question, because I feel like there is going to be a longer. So I just asked one smaller question on understanding the physics, and then I think somebody else can. So can you go to slide 20? Because slide 20. Okay, this is okay. It's this.
20 is right?
Yeah, 2020.
Okay.
Yes. So I have like two questions in here. One, you have this profile which goes like this, and the max is not at the wall, and I wanted to understand this on a physical perspective. Why is the max temperature not at the wall?
Well,
Because
But yeah, don't look at me like he's gonna answer for sure.
I
Go ahead.
no, this is the main point I tried to convey. So the fact that you have colder temperatures than the recovery temperature forced the profile to do this turn. And you see now they are rescaled. Let me show you before. I think no, I'm going backward. Sorry, I think I'm mistaken. So
you have this.
So okay, let me go back here. So the fact that you do have a cooling of the wall and the wall temperature is lower than the recovery temperature forces the temperature profiles to make a turn and give rise to a maximum. And then the real nature of this maximum is connected to the fact that we do have aerodynamic heating.
So there is a generation.
Yes.
There is a heat generation.
Yes.
Like, I mean, that's, I guess at like one side, you're decreasing the velocity, so you're turning kinetic energy to thermal energy, and so you have a peak. But this is counterbalanced by the fact that you're cooling at the wall. So you have these two things, like if you are not cooling, temperature will increase because you're decreasing velocity and decreasing temperature.
I see.
If you're decreasing the temperature at the wall, it's trying to push back this behavior.
I see. And what does the terminology recovery temperature imply?
So the recovery temperature, I try to define. I know that's a lot of terminology, but I try to define at the beginning, and it's some sort of stagnation temperature. So you see here there is a static temperature that is summed to a kinetic term, and this is really similar to the stagnation temperature, apart from this R that is the recovery temperature factor that is due to the non-isentropic process. But you can see it as the temperature that is the fluid reaches when it's brought to rest by the friction of the wall in this case.
Sorry,
Yeah.
brought to the rest.
Yeah, the recovery temperature is the temperature that you reach if you turn all the kinetic energy into thermal energy. That's the idea.
And that's what definition is the recovery temperature.
Yeah.
Okay.
Yeah,
I can see. I see.
Yeah, stagnation temperature.
Yeah, but
I see. Like I see now. I see.
Thank you for your questions.
Yeah, sorry.
No, it was interesting.
Interest? Yeah, sure.
How do you deal with the hybrid parallel architecture you showed about API and CUDA?
Yes. So this code is parallelized with CUDA and CUDA Fortran. So we have a Fortran code. So we have some flags in the code that can turn in the. You can choose to use the code only with CPUs. But if you have the architecture to the GPUs, you can activate these flags, and it will automatically turn into parallelizing GPU.
Like the whole code runs on the GPU,
yes,
or just part of it?
No, the whole code. Yeah.
I was wondering how it could fit like 28 billion.
Yeah.
See the GPU.
No. We are using that. So I remember with my phone one at Cineca for the case that when we video we were using 256 nodes, so 1,000 more than 1,000 GPUs. There's a thing with post processing was a really painful.
Must be parallel.
Yeah.
What the flex is. Okay, so
You're
yeah.
using char areas for this or?
No. The solver is called streams. It's, yes. Develop
There is no separation in any of those cases, right?
No, these are zero pressure.
So any question from online? Okay, well, actually, like I have one last thing. I
Yeah.
was wondering. Yeah, I mean, when you're doing compressible wall models, the matching point, you kind of know where it is because you are like, you know the profile of velocity, you know the log law, etc. But here you have like a lot of different boundary layers.
Yeah.
Let's say you have the thermal boundary layer, and even like have a chemical boundary layer. So I was wondering like on how you pick the matching point and like if you, I mean, in general, like to maybe like try to pick the one characterizing the sharpest boundary layer, or it's based on the velocity field and whatever.
But actually, when you go to wall modeling, it's very tricky because you wish that you choose the same point that you choose for a priori analysis. So let's say you would like to have a matching point at y plus 100. You would like to have it, but you don't know the y plus until you have the shear stress. So, so in the model we provide that. So what is done in general is that you will select the first node above the wall, or the second one, depends on the order you.
Yeah, but you make the mesh, so you should like think about the mesh based on what you expect.
But to be honest, at the end we thought that even by just selecting the first point and having the first node to fall above the temperature peak was really enough, because the number of points you have to fall below, for example, the temperature peak are really extreme. So just a small help will be of relevance to help the time to solution. So, but really, these models should be working well as long as you are in the vicinity of the log lane.
Sure. Okay, yeah, that's it. Okay, so if there's no other question from here or online, we can thank again Michele for the presentation.
For the invitation.